Today we're going to talk about permutations, and the way we're going to think about them is as seating charts. So pretend that 3 pirates walk into a bar, or in general we're going to have N pirates walk into a bar. And let's suppose there's one bar and they want to sit at the bar. How many different ways can we do that? So that's the question. How many ways can they sit at the bar? So the bar is one long line, and now we have these 3 pirates, and the order we currently have them in is we have the red one, the green one, and the blue one are now lined up at the bar. But that's not the only way we could have done it. And what we want to do is be systematic and think about how many different ways could we have lined them up. Well, let's suppose that the red ninja pirate walks in first. So he's going to sit at the bar first. Now, how many choices do we have? We could have the green come and sit next to him, or the blue guy could come and sit next to him. So there's 2 different ways we could do that. Okay, or the red guy could maybe not come in first, and maybe the green guy comes in first. And then you can see that there's sort of a recurrence happening here. We could do blue and red, or red and then blue. So there are 2 ways, again, that the green pirate can come in first. And then his friends can sit next to him in 2 ways. And then, of course, the blue pirate ninja can come in next. And his friends, again, have the same choices for sitting next to him. So these are the 6 ways that we could line this up. And we've seen before 6 come up a lot of times. This 6 is different from the binomial coefficient 6. This 6 is actually the n factorial 6. And the reason is because there are n choices for the first person. And this is the person at the edge of the bar. And now who sits next is, well, there are 1 fewer choices for the second person. And there's 2 choices for the penultimate person. And there's 1 choice for the last person. So we get n factorial equals n times n minus 1 times 2 times 1. And that's a familiar formula for the number of permutations or linear orders of n people. But now let's suppose that the pirates are going to be a little more exciting, and they're going to come with their dad into a restaurant. And now they have a table. And so now we say, okay, well, the pirates, well, they're pirate ninjas, so they're going to knock the table over. But now they need to be arranged around the table. And now I'm going to assume that rotating the table doesn't change the ordering, right? How many ways can we do this? This is a slightly different problem. So we want to think about what's changed and how can we think about this problem of how to arrange the pirates around a circular table. So now it's a similar problem. We have n people seated around a round table. In how many ways? So of course the problem's changed slightly. Instead of these linear orders, these people sitting at the bar, I've got them sitting here, and so there's some symmetries involved. And there are different ways that we could think about this. So we could think about taking the linear orders and then dividing by sort of the number of ways that we can map a circular table onto a bar. Or we could just try to count it directly by sort of unraveling this. And there's sort of 2 ways to think about it. So the way that I'm going to think about it is I'm going to think about Mr. Hat here, who's sort of a canonical choice. It could be the number 1 if you're thinking about permutations in the classical sense with numbers. But if I think about the hat guy, so I'm going to draw him here. Here's my hat guy. And I think about who's sitting clockwise of him. It's the blue ninja. And then clockwise of that is the green ninja. And clockwise of that is the red ninja. And then no matter how I shift this around, I still have the same orientation and the same relative positions. But then if I do this and switch the blue ninja with the hat ninja, now I get a different orientation. And again, I'm going to write it down with the hat ninja. And then who comes next? Now it's the green ninja. And again, next, because I'm choosing to go clockwise. I could have equally chosen to go counterclockwise. As long as I'm consistent, it doesn't much matter. And this is a different arrangement, okay? And then I could continue moving my guy around. I could switch these two, and I can do all kinds of things to get new arrangements. But the point is that if I think about the hat guy as the first thing, then what do I get afterward? Any of these 6 permutations. So when I have n people seated at a table, I'm going to get n minus 1 factorial ways to arrange them at the table, because I choose one person to say, okay, that's the person sitting at the head of the bar. If I remember my bar, I sort of say that's the person I'm going to put here, and I'm going to unravel this table. I'm going to unwrap the table here. Another way to think of the same concept is that we can do a mapping from round tables to bars, and we could obviously go around the other way. And if we do this, then if we're going to unwrap it, we choose a person here to unwrap, and then we sit them at the bar. But that choice of a person, saying the big hat guy, is exactly what makes me lose 1 degree of freedom. So if I take the round table, I have to choose. There are n choices for the head of the table, head of the bar, when I do this projection mapping. And so what I get is the number of bar orientations, which is n factorial, divided by the number of choices, which of course, if I expand out n minus 1, the n's cancel, and that's how I exactly get n minus 1 factorial. So if I'm thinking about round table configurations, I'm going to have n minus 1 factorial of those. Bar configurations, I have n factorial. And then the next thing that we're going to do, and think about this before the next video, is what if I walk into a restaurant with a lot of round tables? How many ways can I seat people at those tables? So we're going to do a seating chart problem after this.